Hello and welcome to Electromagnetics 1. Chris Trampel here. Today we're going to be talking about the electrical properties of materials. Well, we're going to divide all materials in terms of their electrical properties into three broad categories based on how well they conduct electricity, essentially. The conductivity parameter of interest has a symbol sigma. So if you have a large conductivity, a large sigma, we call that kind of material a metal. We consider it a metal. Copper, silver, gold, all of these are metals. And then we also have insulators, which have very small conductivities, much less than 1. Glass, plastic, those are typical insulating materials. And then we have a class of materials called semiconductors whose conductivity is smaller than metals but larger than dielectrics. Okay. The major difference between metals and insulators is simply the number of electrons available to conduct current. Metals have electrons in the conduction band, or so-called conduction band electrons, and dielectrics have primarily valence band electrons, which are more closely tied to the nucleus and don't contribute to conduction currents. So that's the the 2-minute physics behind why some materials conduct electricity better than others. Well, what exactly is current? What exactly is electric current? The current, units of amperes, through a given area is the electric charge passing through the area per unit time. Okay, so we have a two-dimensional region now, a small area, and if you simply sit there and count the number of charges that pass through that area in a given time, that's an approximation to this current. And if we make it mathematically precise by taking limits, we say that the current is simply the time rate of change of the charge, okay, dq dt. If current delta I now flows through a planar surface delta S, we can define something called the current density, okay? The current density, which is simply this ratio here, delta I over delta S. Again, if you take limits, you end up with di ds, essentially. All right, how much current flows through, again, a small two-dimensional region. That's called the electric current density. And it has units of amps per meter squared, or amps per square meter. Okay. We can rearrange this equation a little bit and integrate, and you'll see that if you integrate the electric current density J over the surface area, you will get the current flowing through that surface. Okay. Now, recall we've seen this J before. It appears in Ampere's law, so it's one of the terms in Maxwell's equation. So we can now have a mathematically precise definition for one of those terms in Maxwell's equations. Okay. Well, there's two basic kinds of currents that we encounter. One is called convection current, and the other is called conduction current. Convection current occurs when current flows through an insulating medium. And so I think the best example of a convection current is a moving charged fluid. So if you have a fluid that contains ions and simply is moving from A to B, you're going to have a convection current. Well, let's look at this little this small region here. We've got a little volume of space, and this cross-sectional area here we're going to call delta S, and this length we're going to call delta Y. And we're going to say that there's a volume charge density here in this region, rho sub v. Okay. Well, we're going to write the velocity of the charges here, u, as just u sub y, y hat. In other words, the charges are only flowing in the y direction, and we're going to say that this cross section is so small that we can treat this velocity as constant over the cross section. Okay. Well, going back to our previous slide here, we have this expression for delta I. Okay, the amount of current that's going to flow through this surface area, and we decided that was delta Q over delta T. All right, the amount of charge per unit time, and delta Q, the amount of charge in this little box right here of length delta Y and cross-sectional area delta S, is simply given by the volume charge density times this little volume, which is delta S times delta Y. So this top term gives you the amount of charge in here, and we could rearrange this just a little bit here and say that delta Y over delta T, again in the limit, that's dy dt. That's just simply this velocity term in the y direction. So delta I, the amount of current here flowing through this cross-sectional area, is related to the volume charge density, the cross-sectional area, and the velocity in a direction normal to that surface. Okay. All right. Well, again, from the previous slide, by definition, the electric current density is delta I over delta S. Okay. And so we can simply divide this equation here by delta S. The delta S's cancel, and we get an expression for our electric current density, which is equal to the volume charge density times the velocity of the particles. And so for just to generalize this to any direction, it just turns out that the convection current density J here is equal to the volume charge density times the velocity, wherever you happen to be. Again, I is the convection current, and J is the convection current density. Okay, again, J has units amps per meter squared. I, of course, just has units of amps. Well, for the purposes of this class, we're going to be mostly concerned with conduction current. And this is the second type of current that we encounter in EM. Conduction current occurs when an electric field is applied to conduction band electrons in a conductor. So you don't need a conductor for convection current, but you do need a conductor for conduction current. Okay. Well, let's just consider a single charged particle here that carries charge minus E. Okay, so a single electron essentially. And so by Coulomb's law, the force on the electron here, or I should say simply by the definition of the electric field, force on the electron is the minus its charge, little e, times the electric field that exists at that point, capital E. Okay. From Newton's second law, we can write an equation that involves the force here on the right-hand side, and on the left-hand side, that force has to be equal to, from Newton's second law, the mass times the acceleration. Okay, force is equal to mass times acceleration, and so small m here, this is the mass of the electron, and this tau parameter down here is the average time between collisions. So remember, this electron is going to be propagating in a material, and so it's going to be bouncing off of and colliding with other particles as it moves. And so we attach a parameter to that movement, and we call it tau, which is simply the average time between those collisions. Okay, so if you look at this dimensionally, velocity divided by time, that's going to get you acceleration here. And so we have mass times acceleration is equal to the force felt by the electron. We can rearrange this equation and get an expression for the velocity of the electron, which looks like this. Okay. Well, let's say that we have a number density n electrons per unit volume in our dielectric material now, or I should say, excuse me, in our conducting material. So we've got n electrons per unit volume in our conductor. Okay. So again, simple dimensional analysis tells us that we can write an expression for the charge density of the conductor is simply equal to, again, charge times it's the number unit volume essentially here, like this. So n times minus e gets you the charge density in our conductor. Okay. Well, by definition, again, we saw in the previous slide that the current density here, J, is equal to our volume charge density times the velocity. So we can substitute this expression in here for our volume charge density and this expression here for our velocity, and we end up with the following. The electric current density is equal to NE squared tau over m times the electric field. And we're going to make a definition. We're going to say this parameter here, the number density, the square of the charge in the electron, times tau divided by the mass of the electron, is equal to the conductivity of the material. Okay, and the symbol we use for conductivity here is sigma. So basically, J is equal to sigma times E, and this is the so-called Ohm's law. This is Ohm's law right here. As you can think of it in terms of V equals IR, Ohm's law from circuits. Okay, only the electric field would play the role of V, J plays the role of current, and sigma plays the role of the reciprocal of resistance. We'll see more of this here in a moment. But this is how we state Ohm's law in an electromagnetic context. Okay. So the conductivity of a material, at least in a classical sense, has to do with how many electrons are there per unit volume. Okay. Everything else being equal, the more electrons you have per unit volume, the higher the conductivity of the material. Okay. And it has to do with tau, the average time between collisions. If the electron doesn't collide with another particle as frequently, it makes a certain amount of sense that it's not going to encounter as much resistance. In other words, if tau becomes large, that means the electron fairly infrequently collides with another particle. Okay, so that would also makes sense that if tau is large, we're not colliding very often with another particle, then it's fairly easy for the electron to move through the material, and therefore, again, the conductivity increases. So you can see a lot of physics just right here in the expression for conductivity of a material. Well, let's have a look at a limiting case here, which is that of a perfect electrical conductor, or a PEC. That's the definition, or PEC. You'll hear me use that abbreviation. For a PEC, the conductivity is infinite, and it works out that perfect electrical conductors cannot contain any electrostatic field within themselves. Why is that? Why is there no electrostatic field inside of a PEC? Why is E equal to 0, rho V equal to 0, and the potential difference all equal to 0 inside a PEC? Well, let's say that we take a perfectly conducting material such as this one, and we apply an external electric field across that material. Okay. What happens in a perfect conductor is that there's no resistance at all to the movement of electrons. So what happens is charges are pushed essentially by the electric field, and so you have a charge density here, a positive charge density that builds up on this side, okay, and you have a negative charge density that builds up on this side. So inside the material, you have the original electric field plus an induced electric field that is equal and opposite to it, okay, exactly equal and opposite. So when we add the two up inside the conductor, the total electric field goes to 0. Well, of course, in reality, all conductors are imperfect. In other words, they have a finite conductivity. So it's useful to study a finite conductor, or I should say an imperfect conductor as well. Let's have a look at this diagram here. This is a little chunk of conducting material that has a finite conductivity here, and we've applied a voltage across it. So this side is at, there's a potential difference of V from this side to this side, and the material has length L and cross-sectional area S, and there is a current I flowing through it, starting to look a lot more like something you would see in circuit theory. Only now we're gonna think about what's happening in terms of fields. Okay, we're gonna say again that this L is short enough and that this cross section is small enough, S, that we can say that the electric field is basically constant across this cross section here. Okay, so by the definition of voltage, remember, is the integral of the electric field along a line, and so we're going to say the line is just running right through here. We have a line of length L. So we can say EL is equal to V, or the electric field is equal to the potential divided by the length. Okay, just very, very simply. Again, we have another definition here for the magnitude of the electric current density. Again, the current divided by the cross-sectional area, amps per meter squared. If we substitute in now for J using Ohm's law, we're going to get this equation. I over S is equal to sigma E, which is also equal to, substituting from here for E, is equal to sigma V divided by L. All right. So interestingly enough, if we rearrange this equation right here and we solve it for the potential V, we can say that the ratio of V divided by the current, I should say, if we look at this equation and I should say this left-hand side and this right-hand side here, and we solve for the ratio V over I, we find that V over I is equal to L, the length of our conductor, divided by sigma times the cross-sectional area. Okay, and this V over I, this is literally resistance from circuits 1 right there. That is resistance. That's the formal definition of resistance in terms of electromagnetic parameters. Okay, in other words, in terms of the conductivity of the material. The reciprocal of the conductivity is called the resistivity here. So you can write the resistance in terms of the resistivity times the length over the cross-sectional area, or the length divided by the conductivity times the cross-sectional area, however you want to do it. But this rho sub C is just the resistivity. It's just the reciprocal 1 over sigma, just the reciprocal there. Okay. So this is a way to characterize materials. This is a way, again, to characterize if you have a conductor of a particular length that's thin enough, you can characterize it using the resistance parameter from circuits. Well, okay, so the second big kind of material we want to talk about here are insulators or dielectric materials. Okay, how do electric fields interact with dielectric materials? Well, let's consider an atom of the dielectric as consisting of a negative charge minus Q, the electron cloud, and a positive charge plus Q, the nucleus. Okay, so here is our original one atom of our dielectric. Essentially, you've got a nucleus that's positively charged, and there's a negatively charged electron cloud around it. So what we're going to do is we're going to apply an external electric field to this atom, all right? And when we apply an external electric field, the positively charged nucleus feels a force in one direction, and the negatively charged electron cloud feels a force in the opposite direction. And so essentially the electron cloud gets distorted, all right? And we call that distortion polarization. Well, it turns out that by the principle of superposition, we can write an expression for the field here, the total field here that exists, as a sum of the original, I should say, we can write an expression for the polarized charge density as the original charge density plus a little dipole that has moment q times the distance between the positive and negative charges d. So a dipole of moment qd here. So if we add our original electric field, or I should say our original charge distribution to this charge distribution, we will get our polarized charge distribution. So what we're trying to say here is that the effect of applying an external field to an atom is essentially, it's as though you've added a little dipole field to the original field. That's essentially the idea, okay? And if we have capital N charge dipoles, so if you have capital N of these guys per unit volume, we define a polarization vector capital P that's just simply equal to capital N times small p, just like this, or NQ times D. So this is a vector that allows you to deal with macroscopic volumes of things. Okay, so usually a dielectric consists of many billions and billions of atoms, so we don't want to just work with one like we would here with small p. So usually to work with a practical material in macroscopic electromagnetics, which is what we're doing in this course, we have to define again a sort of number density capital N, which is the number of dipoles per unit volume. Again, so if your material is more densely packed with atoms, other things being equal, your polarization vector will be larger. Similarly, if the positively charged nucleus and the negatively charged atoms are more weakly tied to each other, in other words, if it's easier to stretch them, then this D will increase. Okay, so depending on the kind of atom you have, there will not, I should say, not all atoms have the same attractive forces between the nucleus and the electron cloud, and so that's another parameter that goes into materials, is how closely bound are the electrons, and that varies from material to material, and that property affects their electromagnetic properties, their electric properties. Okay, so how strongly bound those electrons are affects the electrical properties of the material through this equation right here, through the polarization vector P. Well, what's the effect of this polarization from a potential or from a field's perspective? Well, it turns out that when you polarize a dielectric, what you're doing is creating equivalent charge densities, essentially. That's what you can think about it. That's one way to think about what you're doing. You're creating some equivalent charges, okay? There are two different kinds of equivalent charges that you can make. You can create an equivalent polarization surface charge, rho sub ps, and that is simply equal to the polarization vector dotted with a normal to whatever surface we're talking about. So if we have a volume bounded by a surface, again, I should say consider a dielectric, I should say, of certain volume that has a surface, and we apply an electric field to it, then what we're going to get are, on the surface, we're going to get some equivalent surface charge density. Okay, that is equal to this polarization vector dotted with a surface normal to that surface. Okay, and then inside the volume, we're going to have an equivalent volume charge density, which is equal to minus the gradient of the polarization vector. Right, and those equivalent surface charges and equivalent volume charges actually create a field. They create a potential. And all I'm doing here, you'll recognize these expressions from the lecture where we talked about the electric potential and how you can integrate surface charges to you can find the potential due to surface charges. That's this integration. And you can find the potential due to volume charges. That's this integration. If you'll notice again, the potential falls off as 1 over r here. Okay, and all I've done here is substitute into those expressions. If you look up in your text, there will be a rho sub s here, and there will be a rho sub v here. And in our context, because we're talking about equivalent surface charges, rho sub s is just p hat dot n hat prime, and rho sub v is minus the gradient of the polarization vector p. Okay. So if you know, given an electric field, an incident field, an impressed field, if you know what the polarization density is throughout the entire volume, you can calculate the potential at a point by integrating the potential, I should say, due to the polarization, by integrating over the surface this quantity, integrating through the volume this quantity. Well, we have another important quantity that has been appearing in Maxwell's equations that we haven't defined yet, which is called the electric flux density. And the reason we haven't defined it is that in order to have an electric flux density different from that of free space, you need materials. So let's consider a dielectric region, again, a material that has a dielectric material, that has an insulating region that has an insulating material in it. And let's say that it also now contains some free charges. Okay, so we have within our material, we have atoms that have a positively charged nucleus surrounded by a negatively charged electron cloud. Okay, and then also we have some electrons that aren't bound to a nucleus and can move around, and those are considered free charges. So we're going to say we have a region that has both of those. So let's say rho sub v is the volume density of free charge. Then the total volume density will be the sum of the free volume charge density and the equivalent volume charge density. So that's what this equation right here says. The total charge density is the charge density due to the free electrons and the charge density due to the bound electrons, or the equivalent charge density, if you want to think about it like that. Okay, so we can solve here for our free electron charge density just by rearranging this equation. And then if you remember, we have an expression for this equivalent charge density, which is equal to minus the gradient of the polarization vector. So I make that substitution for this term here, and what pops out is that the free electron charge density is equal to minus the gradient of the free space permittivity times the electric field plus the polarization vector P. And so what we do is we define this quantity in parentheses to be the electric flux density. That's a definition. The definition of the electric flux density D is free space permittivity times the electric field plus whatever polarization whatever polarization vector you have at that point in space. Well, what else can we do with this? It turns out that in some dielectrics, the polarization vector P is proportional to the electric field. Okay, this is a this is an equation that holds for some but not all electric fields. So we say the polarization vector P is somehow proportional to the electric field, which makes a certain amount of sense. I mean, it makes sense that, for instance, as you increase the electric field, the atoms should be stretched more, and therefore the polarization vector should increase as well. So it makes qualitative sense to do this, and this constant of proportionality here, chi sub e, is called the electric susceptibility. So this is just a way that we can relate this polarization vector P to the electric field. For a lot of materials, this works well. And so we can make the substitution for P into the definition now of the electric flux density D, like this. And so we find that the electric flux density D is equal to the free space permittivity times 1 plus the electric susceptibility times the electric field. Or we can write it simply as D is equal to epsilon E, okay? Where this is equal to now the permittivity of the material, essentially. It's not permittivity of free space anymore. It's the permittivity of this particular dielectric material, okay? And it's equal to the permittivity of free space times a constant here. And this constant, epsilon r, is called the dielectric constant, or the relative permittivity. And it's given by the equation 1 plus chi sub e, and it is the ratio of the permittivity E to the free space permittivity. Okay, well, in subsequent lectures, we're going to be using many of the quantities that we've defined in this one. So I hope you understand the electrical properties of materials somewhat better, and I'll see you in the next lecture.